the assignment that is due today is 5.4. And 5.4 is on connecting graphs of your function with the derivative function with the second derivative. Now, just as a quick reminder, let's look at what it means to take the derivative of a derivative. And one way we can look at that is by in physics. In fact, primarily that's where calculus came from. Sir Isaac Newton, he did not care about the math. He was trying to explain his ideas, he was trying to prove his ideas on motion. And so if we look at something like, I don't know, some graph that looks, let me make this a little different. How about something like this? And we'll say that the x-axis is time and the y-axis is distance. And we'll call this equation our S of t, which is what is called a position function. Why is it called a position function? For any time, say 1, 2, it will tell me the position of a particle, right? It'll tell me my position. Now, how would I take the derivative graphically of this? What do I do to take the derivative graphically of this function? Right, so I see, it looks like I have an instantaneous rate of change right here of 0. So we'll just call that, since we're looking at the graph of the derivative, that is right here, it's a slope of 0. And if the graph represents my slope at any given time, then that would be an x-intercept. Okay, what's happening on this side of my 0 slope? Yeah, it looks like it's positive. So if it's positive, it has to be above the x-axis. So I don't know, something like this. What about on the other side? We see that the slope is gradually getting steeper and steeper. So we'll show that by going further into the negative for our derivative function. So we'll just continue down like this. Does it surprise you that this, what sort of looks to me like a quadratic, that the derivative is linear? Why not? Yeah, so Eleanor said because of the power rule, we subtract 1 from the exponent, which makes sense then. If we have a quadratic, we subtract 1 from our exponent, that makes it linear. Okay, so this is going to be, this is my graph, my v of t, or this is our first derivative. So v of t is, well, what? When we talk about slope, when we talk about the slope at any given point of a position function, the slope is going to be, well, slope is defined by rise over run, and the rise in units is what? Distance, and the run is time. Distance over time is what? It's velocity. Yep, so this should give us our velocity. And we'll say distance, I don't know, distance is in maybe meters and time is in seconds. So meters per second is a type of velocity. Now I want to take the derivative of the derivative, and my derivative is this, the derivative function is this blue line. And if I take the derivative, it looks like the slope is constant. Right? Our slope is going to be the same regardless of where we are. The slope is what? The slope of our slope is what? Positive or negative? negative. And since it's always going to be the same, then the derivative of the derivative would look maybe something like this, where that derivative function, this is my a of t, and it's always negative. Our rise over run is always negative when we read it from left to right, so it should be a line. It's always going to be a constant too, of a horizontal line below the x-axis. Now, when we take the derivative of a derivative, so for the blue graph, our y-axis is no longer distance, it's what? It's velocity, which is not the acceleration. That would be maybe meters per second, right? Velocity. Now, if I do my slope of rise over run, and my rise is meters per second over what? What's my run? Is my run is seconds, and seconds is the same thing as seconds over 1. When we divide by fractions, here's a tip. Keep, change, flip. So I have meters per second times 1 over seconds. What does that give me? Meters per second squared, which is what? Acceleration. So my a of t is acceleration. Acceleration. All right. It's just sort of an idea of how to wrap our heads around this connection between our function versus our derivative of that function versus the derivative of the function. Okay, now let's go back and talk about some ideas, some important ideas that we talked about in previous sections before our holiday. And one of them was called the first derivative test. I think this was 5.2. In 5.2, when we talked about the first derivative test, what is it? First derivative test. Do you remember, or can you find the first derivative test in your notes?
What's it, the monotonic property?
Yeah, it just talks, and monotonic properties are what?
Where the graph is increasing.
Yeah, so the first derivative test just tells me where the graph is increasing and decreasing. So tells us where the graph is increasing or decreasing. These are called monotonic properties. The properties. Now, an important reason why we want to know when the graph is increasing and where it's decreasing is that transition between where we increase versus decrease is what? It's a what? It's not an inflection point. It's a maximum. It's a max. So if I can tell where the graph, the monotonic property is with the graph where it's increasing and decreasing, I can find maximums. I can also, where the graph is decreasing versus when it's increasing, that transition point would be a minimum, in this point, a minimum. So that's sort of the point of why we use the first derivative test. And we use a sign diagram to help us identify those points. Bless you. Now, with a first derivative test, is it guaranteed where my slope is 0? Is it guaranteed that that's a max or a min? No. What's another possibility besides if I have a 0 slope? What's another possibility besides a max or a min? It could be a stationary inflection point. Yeah. So we could end up having what is called a stationary inflection point, and we'll talk about that in just a moment. I do want to talk about the second derivative test. Now, the second derivative test is, well, what happens when we take the second derivative? And there's something interesting that happens. Gosh, it's noisy. I'm going to go shut the door. There's something that's interesting that happens with what is called the concavity of the graph. With the second derivative test, I can discover something about the concavity of the graph. In fact, that's what the second derivative test is all about. In fact, I'm going to write that down right here. So the second derivative test tells us the concavity of the graph. Tells us where the graph is concave up or down. So the first derivative test does what? What does the first derivative test even tell us? What does a derivative tell us to begin with? It tells us the instantaneous rate of change. Yep. The whole point of a derivative is to tell us the instantaneous rate of change. The first derivative test, because it tells us the instantaneous rate of change, it can tell us where the graph is increasing and decreasing. And where we have a zero slope, that tells us that we may have a potential maximum or minimum. Now down here where we talk about concavity, the concavity, let's look back up here at our first graph we have here. According to the red graph, what we started with, our position function, does that look like it's concave up or concave down? It looks like it's concave down. Yeah, that cave part. The cave part is pointed downward. So we say that that is concave down. Now look at the second derivative. The second derivative is the green graph. Is it positive or negative? It's negative. And in fact, that's if I want to know whether with the first derivative test, whether the slope is increasing, how do I know that? The first derivative has to be what? If it's increasing. And if it's decreasing, then the derivative is negative. If the second derivative test, the point of the second derivative test is to identify this concavity, then from our first graph, what do you think when the second derivative is less than zero, what that means? If the first derivative, if it's greater than zero, that means what? It means isn't the first derivative, doesn't that tell me the slope? What is it telling me about the slope? Slope is positive. Slope is positive. Okay, what if our first derivative is less than zero? Slope is negative. Okay. Now, am I going too fast? Am I getting too messy? Is that better? If our second derivative is less than zero, what does that mean? It's concave down. That's what we found up here. Our second our second derivative is negative, so it's concave down. The whole point of our second derivative test is to identify the concavity of the graph. So this is concave down, which means then that if our second derivative is greater than 0, that means what? Concave up. Concave up. So what could potentially be when our second derivative is equal to 0? What is if this concavity switches at a 0 point where we go, our second derivative goes from negative to positive, there's a special name for a point where the concavity of the graph changes. It's called an inflection point. Yep. So in between the change of concavity, that is called an inflection point. The point in between the change of concavity is called an inflection point. Well, why be all wordy like this? Why don't I just say f prime of x, f double prime of x, when it equals 0, it is an inflection point. Why don't I say that? Am I guaranteed an inflection point when the second derivative is equal to 0? Am I guaranteed a max or a min if our first derivative is equal to 0? No. Do you think I'm guaranteed an inflection point when our second derivative is equal to 0? How do you test it? How do you test to see if it is an inflection point? You have to use a diagram that starts with an S. You have to use a sign diagram. For all of these, you have to use a sign diagram to determine whether we have a max or min. We have to use a sign diagram. We also have to use a sign diagram to determine whether our graph has an inflection point. So let's talk about this first. So our first derivative test. First derivative test. What does it tell me? If the slope changes from, in this case, negative to positive, then that point is a min. If our slope changes from positive to negative, then that point is a max. It can also tell us if we have a positive and a positive, if we have a positive slope followed by a positive slope after an instantaneous rate of zero, instantaneous rate of change of 0, then that would be a what? Yeah, that's a stationary inflection. So it could also tell me if I have something like this, where I have a positive slope followed by a positive slope, that tells me a stationary inflection. Or if we go from negative to negative, that's also another stationary inflection point. These are not maximums and they're not minimums. Now with my first derivative test, I can identify all of these based upon the slopes. For my second derivative test, what does the second derivative test do? What's the point of the second derivative test? It tells us the concavity of the graph. Yeah, it tells us the concavity of the graph. So I'm going to write this over here for the second derivative test. it tells us the change in concavity if our graph goes like, I don't know, something like this. These are non-stationary inflection. Why are these non-stationary inflection points? What makes them non-stationary and what makes these stationary? Yeah, when the slope is 0, we have a slope right here, an instantaneous rate of change of 0 here and here. Here we don't have an instantaneous rate of change of 0. You can see that that's a negative right there. At that inflection point, we have the slope is negative, and over here it's positive. Yep, correct. So, do you think our second derivative would be able to identify these as well? The stationary inflections? If we look at these graphs, do the concavities change of the graph? Yeah, they do. So because the concavity changes, then that's also going to be, we'll also be able to see that with our second derivative. Now the second derivative, if what would the second derivative have to be if we have concave down? It'd be what? It'd have to be negative. Yep. So we'd have this side over here would be a negative slope. And over here, I have a concave up, which would be what? Positive. Over here, this is concave up. So that one would be positive, followed by a concave down, which is negative. So this one over here would be negative. For our second derivative test, and we use the sign diagram, what should we find over here? What would this one be? For our second derivative test, is it still positive followed by a positive? For our second derivative? For our second derivative, what would this side be over here? That would be negative because it's concave down. Over here, what would that one be? Yeah, it's concave up, so that would be positive. What about this one here? If this piece over here before the inflection point would be what? It's concave up, so it's positive. And this one here is concave down, so it should be negative. I hope you understand the I've color coordinated this. So everything in red indicates the second derivative, and everything in black over here represents the first derivative. I don't know if that's confusing to you, but nevertheless, we can still, this is sort of the relationship, I'm going to leave that in there. That's sort of the relationship between the first derivative and the second derivative as far as understanding our graph. All right, should we do an example? Okay, let's do an example. I want to find all maxes. Find all maxes. Is it just with an X? Maxes and mins and inflection points gosh, that's sloppy. Inflection points for f of x equals x to the power of 4 minus 4x cubed plus 2. where do I start? Josh, where do I start?
Use the record derivative.
Yeah, so we're going to take the derivative, and when I take the derivative of this, what do I get? Yeah, actually, I wanted to use a different color. Let's try red. Okay, so I'm going to take the derivative. What do I get?
Prime of x equals 4x cubed minus 12x squared.
Okay, now what? What do I do now? The goal is to find the max and mins and the inflection points. Eleanor, any ideas? Yeah, so we need to know when the slope is 0. We need to know what x is when the slope is 0. So we're going to say that the slope then is 0. And how would we solve for x if that side over here is 0? Yeah, let's factor. Can I factor anything out of both of these terms? All right, a 4x. How about a 4x squared? 4x squared. If I factor out a 4x squared, what's left behind? Okay. So what are my critical points? Critical points don't mean a max or a min or an inflection point. A critical point means something I need to look at. What are my critical points for my sign diagram? Okay, I agree with you. 3 is a critical point because if this x is 3, then 3 minus 3 is 0, and anything times 0 is 0. So I have 0 equals 0, which is an equation. So one answer is 3. What's another one? Yeah, if this x right here is 0, then we get 0 as well. So another critical point is 0. Does that mean that one of these is a max and one is a min? No, I'm not guaranteed that because there's other possibilities of what could be going on there. Okay. Right now what? What do I do from here?
You plug in points on either side of critical points to figure like slope would be positive or negative.
Okay, so what's a number that I can plug in that would represent this interval from negative infinity all the way to 0? All right, yeah, let's try -1. So try x is -1. I'm going to plug that into here. Is that positive or negative? It's, yeah, because we squared, it's always going to be positive. So that's going to be positive. What about when I plug this into here? What does this become? A negative. So if I have a positive times a negative, what does that give me? Yeah, that means that everything on the left side of 0 has a slope of what? A slope that is what? It's negative. It's a graph that's going to go down. It's negative, 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 negative all the way to this point. What's happening when x is 0? We have a slope of 0. And then I don't know what happens next. Do I go back up or do I go back down? I don't know. I don't know. We have to find out. So how do I find out? How do I find out what kind of slope I have here? Okay, yeah, we just tried. Could I try 2 or 2.5? Could I try 2.999? Yeah, any number here, any number in this interval will work. So we want to try, in this case, what did you say, try 1? Okay, we're going to try 1. If we take that 1 and plug it in here, is that positive or negative? What is it? If I plug this 1 into here,
Oh, well, and there we get 4. Then.
so that's going to give me a positive number, right? So I don't really care what the slope is. I just care whether it's positive or negative. That's why we call it a sign diagram. I just care about the sign. So this part, if I plug one in here, that's going to be positive. And if I plug it in here, louder, negative. What's a positive times a negative? A negative. What's happening when x equals 0? It's a stationary inflection point. Now, Riley, if you wanted to calculate, if I wanted to take that one and actually calculate what the slope is, that's fine. It'll still work, right? If it's positive, then we can then say that all of the values in that interval are positive. If they're negative, we can say the same thing. I'm just trying to make our life easier. Just say, oh, it's a positive or negative. Yep. So, all right, so we have a graph that goes down, down, down. Then there's a stationary point. And then it goes down, down, down. So that makes it a stationary inflection point because we have concave up on this side and concave down on this side. It's a change of concavity, which is an inflection point. All right, so let's find out what happens on the other side over here. What should we try? Okay, let's try 4. So try x equals 4. If I take that 4 and plug it in here, is that positive or negative? Yeah, it's positive. And if I plug that into here, that's a positive. What's a positive times a positive? What's happening when x is equal to 3? It's what? Is it stationary inflection? It's a minimum. We have a graph. We're looking at the slope, right? For our first derivative, we're looking at the slope. So the graph goes down, it goes down, 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 stationary inflection, down, down, down. We hit a minimum and then we have a slope that's positive all the way back up. Is this, what's that word to indicate the different kinds of minimums? What are those words that indicate the different kinds of minimums? Local and global. Local is also relative. We can either say a relative or a local minimum. What's the other word for global? Global or absolute. Both are correct. Both of them could be used on the AP test. Is this a local or a global? It's global. It's a global minimum. Is this a relative or an absolute minimum? It's absolute. Absolute and global mean the same thing. I just wanted, you just need to get used to both of the vocabulary words. Okay. So should we graph it? Actually, we want to check for inflection points. We found an inflection point. We found an inflection point here. Could there be another inflection point? Is that possible? Let's find out. Let's find out. How do we find another inflection point? What do we need to do? This is the first derivative test. First derivative test. That hopefully helps us identify our max and mins. What does the second derivative test tell me? It tells us our concavity. Do you think that this stationary inflection will show up for our second derivative test? It should. Yeah, if we have a slope that's decreasing and then we have a stationary point and it's decreasing again, didn't the concavity change? So it should show up again. So here's our second derivative test. Second derivative test. So we're taking the second derivative. What is the second derivative? Actually, I see I have a huge mess here. I don't know where it was. There we go. What's the second derivative? Okay. Now what do I do to execute the second derivative test? Okay, it needs to be equal to 0 and then factor. What can I factor out of both of these terms? Okay, so we have 12x. What's left behind when I factor out a 12x? X minus what? 2. What are my critical points? 2. 0 showed up again. It should, because it's a derivative. I'm sorry, it's an inflection point. It should show up again. Okay, so our critical points, we have 0 and 2. Is it guaranteed that x equals 2 is an inflection point? It is not guaranteed. So we have to test it. How do we test it? The sign diagram. Okay. Let's figure out what's going on over here. How do I figure out what's going on over here? Plug in a value less than 0. What's a value less than 0? -1. So try x equals -1. I plug that into here. Is that positive or negative? Negative. And if I plug that into here, negative, what's a negative times a negative? A positive. What does that tell me that is happening with the graph on the left-hand side when x equals 0? It says concave up. It's telling me it's concave up here. That's what the second derivative test tells me is concavity, not the slope. So it gives me concave up. All right, let's test something. Let's test this side. Okay, let's try x equals 1. When I plug in 1 here, what does this become? Positive or negative? Positive. If I plug it in here, negative. What's a positive times a negative? Okay, which means that x equals 0 is what? An inflection point, right? That has to, we already found that it's an inflection point, but we just found it again. Okay, what about over here? Try what? X equals 3. When I plug in x equals 3 over here, what is that? Positive. And if I plug it in on the other side? Positive. What's a positive times a positive? A positive. So we know we have an inflection point at x equals 0 and 2. Is this x equals 2, is it a stationary inflection point? Why? How do I know that it's not? It didn't show up the first time. Yeah, it didn't show up here, so it cannot be a stationary inflection point. So let's graph this. Let's graph it and see what we found. What kind of function family does this belong to? It's quartic. Yeah, it's quartic. Let's go to Desmos. Okay, we said that x equals 0 was what? We said that x equals 0 is what? Is it a stationary inflection point? Yeah. We also found that our minimum, we found that we have a slope of negative, negative, slope negative, and then followed by a positive, which makes, we decided that this was a global minimum when x was equal to 3. Does it look like we found the global minimum when x is 3? Yeah, I agree with you. Now we also found a non-stationary inflection point when x is 2, when x is equal to 2. So that's, we said we have a non-stationary inflection point when X is, oh, I missed it. Right there. Do you think you could just eyeball this and say, without math, could you eyeball that and say, oh, that's where the concavity changes? You think you could? That looks really, that looks hard for me. I don't know if I'd be able to eyeball it exactly.
For softer.
Without calculus, I think finding that precise point of the change in concavity would be difficult. Does it look like on the left-hand side that we have concave down? Does it look like that? Does it look like it's concave up on the right side? Yeah. Yeah, so that's our inflection point. Now, there's no statistics at all in calculus. You can apply calculus into statistics, but for this course, there is no statistics. But I do want to briefly talk about statistics, and only because of where statistics comes from. Now, it's really cool that this happens so naturally when you look at the height. If our population is substantially large and you're looking at one parameter of one population, then height falls into what is called a normal curve. Intelligence falls into a normal curve. Weight falls into a normal curve. Things that are natural fall into this normal curve. Now, this is our average, our mean, median, and mode. All three of them are the same value for a normal curve. And then there is, if we look at one standard deviation above the mean versus one standard deviation below the mean, that represents how much of all of the data. Does anybody remember the empirical rule? It's 68. It's 68% of the population. And then if we measure out this same distance here, and we measure out that same distance again for two standard deviations. So two standard deviations above and below would represent how much? 95. And then three standard deviations. What's the empirical rule? 68, 95, 99.7. That's the empirical rule. 68, 95, 99.7. Now they have an equation that helps us identify a standard deviation, but graphically, how do you identify a standard deviation? What is happening graphically for a standard deviation? An inflection point. Yep. This point here and this point here, between those inflection points, that represents 68% of the data, always. And then there isn't another inflection point. This is always concave up from then on. But now that we've established a standard deviation, we can use that to measure the next standard deviation and the next after. But graphically, a standard deviation is identified by an inflection point. So that's the only thing I wanted. What is an inflection point? Where the concavity of the graph changes. The concavity of the graph changes from concave up to concave down, or vice versa. Okay, so we're going to do another one. Let's move on. Scroll over. What was that? Okay, I want to, same thing. I want to find maxes, mins, inflection points for g of x equals x to the power of 4. Cool. Chris, I'm suspicious because we don't have a book in this class, but yet you seem awfully entertained with the book back there. We actually do have a book for this class. Did anybody get the book for this class? No, why? Because it's all online, right? I have it all online for you. But there is in the bookstore, you can pick up a book for this class, but why worry about possibly damaging it and then having to be, then you'll be charged for it. And there's no reason for that when everything is online for you. You're welcome. Okay, what do I do first? Okay, if I find the first derivative, what am I doing? What test is this? Yeah, this is my first derivative test. The first derivative test. And the first derivative test, I'm really looking for what? A max or a min, right? Okay, so we're going to take the first derivative, which would be what? 4x cubed. Okay, now what? Okay, so I have 0 equals 4x cubed. All right, what's my critical point? It's just 0. Yeah, so if this is 0 here, then I have 0 equals 0, which is a true equation. So x is 0. And so, in fact, there's only one critical point. Okay, so let's figure out what the slope is on both sides. How do I find what the slope is over here? Hey, Sam. Okay, so try x equals -1. Oops, that doesn't look like -1. If I plug in -1 here, what does that give me? Yeah, it gives me a negative slope. So I have, this is going to be negative over here. What about on this side? It's positive, so I'm gonna try what? 1. And when I plug that in, it's gonna be positive slope, okay? So what does that mean x equals 0 is? It's a minimum. What kind of minimum? It's global, yeah. This is gonna be a negative slope, negative slope, negative slope, followed by a positive slope. Yeah, there's just one point where we get to that. We don't go back down there. So this is going to be a global min. Okay, if we take the second derivative, what kind of test are we engaging in? Yeah, the second derivative test. All right, so this is our second derivative. The first derivative test tells me my slope. The second derivative test tells me my concavity. It tells me my concavity. Okay, so we're taking the second derivative. So I have g double prime of x equals 12x squared. Okay, do I have any critical points? 0 again. Okay. So how do I know what my concavity is on this side of x equals 0? Okay, so we plug in negative, so try x is -1. When I plug that in, what do I get? I get a positive. Yeah, anything squared is going to be positive. So that's going to give me a positive value. And then what about over here? Try what? X equals 1. When I plug that in here, I get positive, which means my concavity on the left-hand side is what? Concave up followed by concave up. Is this an inflection point? No. Are we guaranteed an inflection point when our second derivative equals 0? No, we are not. Let's look at what does this look like? What does this graph look like? Does anybody know? So I have g of x equals x to the power of 4. This looks like this. We said that this was a global minimum. Is it a global minimum? When x equals 0, is that a global minimum? Yes. Now, the second derivative test, we said that it was concave up followed by concave up. Is it concave up followed by concave up? Yep, it is. So all we found really is that this is a minimum. We do not have an inflection point for that. I just wanted that example was meant to show you that we are not guaranteed an inflection point just because we have our second derivative equal to 0. That's not a guarantee. Right, let's do another one. Am I going too fast? I always hated when my teacher went too fast. It's like, oh, I was about to write that down. Oh, shoot. I'm trying to pay attention. And then I write it down. And then halfway through, you move on. And So please advocate for yourself. Say, Mr. Hall, can you go back? Same directions. What are the directions? Find maxes, mins, inflection points. Okay, we used f of x, g of x. Let's try h of x equals x to the power of 2/3 minus 3. Same directions, maxes, mins, and inflection points. More time? Chris needs more time on his book. Emerson, do you have it?
I'm still trying to figure out.
Right, so can't we just use the power rule? So for our first derivative test, we have h prime of x equals what?
I got 2/3 times the cube root of x.
Times the cubed root. Well, if we,
It's all like 2's over that cube root of x.
okay, so if I have y equals a times x to the power of n, the power rule says what? A times x. Okay, if we subtract 1 from this, what do we get? Negative 1/3. So we could rewrite this as 2. What's the negative exponent rule? If I move it to the denominator, right? So I have 3 times x to the power 1/3. Do you remember our fraction exponent rule? Fraction exponent rule, if I have a to the power of b over c, then this becomes a root. What root is it? The cth root of a to the power of b. So I can rewrite this so that I have 2 over 3 times the cubed root of x. Okay.
Yeah, that's what I was trying to say.
Oh, okay. So now what? Yeah, we plug in 0 because that's what I want to know what happens what's the transition from that instantaneous rate of change of 0. So what's an x value that will give me 0 equals 0? 0. So that would give me 0 over 2 times 3 times 0 to the power 1/3, which is 0 in the denominator. So that gives me 0 equals 2 over 0, which isn't that undefined? Is there no value I can plug in that will give me 0 equals 0? There isn't, right? But this is still a critical point. This is still, when x equals 0, that's still a critical point. It is not true that plugging in 0 will give me 0 equals 0. However, it's still a critical point. Why is it a critical point? Because it gives me something that's undefined. Does that make sense?
Yeah.
Okay. So we're going to use our sign diagram with one value. When x equals? Louder? 0. Okay. Now what? How do I figure out this sign diagram? Okay, we want to try x equals -1. When I plug that in to here, what does that give me? Is that positive or negative? Actually, if it helps, you could plug it into here. So what is a cubed root? A cubed root, we're trying to think, so it's of -1, we're thinking of something times something, or something times itself gives us -1. Yeah, the answer is -1. So I have 3 times -1, which is -3. 2 over -3 is positive or negative? It's negative. So we're getting a negative value on this side. What about over here? Yeah, you tried what? Try x equals 1, plug that in. What times itself gives us 1? 1 times 3 is 3, 2 over 3, 2/3, it's positive. So this is going on this side, it's positive. What does this negative mean over here? If this is our first derivative test. The slope is negative, followed by a positive slope. What does that say about x equals 0? It's a minimum. X equals 0 is a min. If I can't plug in anything in here, does that mean that this is discontinuous when x equals 0? Can I plug in 0 here?
Yes.
0 to the power 2/3 is 0. 0 minus 3? -3. So it's not discontinuous, but it's not differentiable. It's possible to have something that is continuous, but not differentiable. Emerson?
Is it like a cusp or?
A cusp or a corner, yeah. Yep. A cusp or a corner, there's one other one. it's the vertical tangent that could also, but a vertical tangent would not be, we don't have a slope of 0 for a vertical tangent. So it's either a cusp or a corner. Now let's explore this further by finding the second derivative. So we're going to do, let's find the second derivative. So now we're going to do the second derivative test. The second, that's sloppy. Second derivative. That's not any better. I am just getting worse. Okay, so here was our first derivative. Can we take the second derivative of that? H double prime of x is what?
-2 over 9 times the cubic root of 4 or x to the or x.
-4/3, okay. And if we wanted to try to, use some of our laws of exponents and move this to the denominator, that would give us something like -2 over 9 times the cubed root of x to the power of 4. Does that look right to you? Is that the same? If we're trying to find, if we're doing the second derivative, what do I need to do now? We need to set this to 0. This is our second derivative. What's an x value that will give me 0 over here? What? So there's no value, right? There's no x value that I can plug in here that will give me 0 equals 0. But if I plug in x is 0, there I get, it becomes undefined. Because it's undefined, it becomes a critical point. It becomes a, oops, I did not mean to do that. It becomes a critical point. So we still have this 0 here. And I want to know what's happening on both sides. If we're using the second derivative, what is it telling me? What am I trying to figure out if we're dealing with the second derivative? The concavity. So what should we try over here? Try x equals -1. If I try -1, I plug in -1 in here. Anything to the power of 4 is positive. So all of this in the denominator is positive. So I have a negative in the numerator divided by a positive, which is a negative. And then on this side, try what? 1. When I plug in 1, x to the power of 4, anything to the power of 4 is going to be positive. So this becomes positive times 9, which is positive. -2 divided by a positive? A negative. So I have, here is x is equal to 0. On this side, tell me about the concavity. And on this side, concave down. So I have concave down followed by concave down. What is this? A cusp. Could it be a corner? Is it possible that this is a corner? Yeah, this is defining it as concave down. A corner is not concave anything. A corner is not concave anything. Corner is not concave. There's no concavity to a corner. So it has to be a cusp. It has to be a cusp. Okay, let's graph it. What's that, Josh?
What do you call it when it's like, you say there's no concavity, or is there a special word for when it doesn't have concavity? Or is it just, would you say?
I'd just say it's linear. If there's no curve to it, it's just linear. So let's just type this in. we have h of x equals x to the power of 2/3 minus 3. There we go. It is a cusp. One more. We'll go to the top. Am I going too fast? You want to go back? Yes, no, maybe so? Everybody's good? Okay. Right, same directions. What are the directions? Yep. Do you want some think time on this? You're trying to find max, mins, and inflection points without a calculator. Okay, let's be 100% sure. What was your first step?
So I took the derivative.
Okay, so if we take the derivative, let me use a different color. K prime of x equals what?
Negative x cubed plus 9x.
Okay, and then
And then so I factored out a,
how you set this to 0.
I set it to 0 and I factored out negative x.
Okay, so I have negative x. What's left behind?
And then x squared minus.
Okay,
And then I factored x squared minus 9, x minus 3x plus 3.
so you identified this as a difference of squares. Okay, so that gave me x minus 3 and x plus 3. So what are the critical points?
Negative 3, 0.
Yeah, so you have negative 3, 0, and 3. And then,
So it's negative 4 for then plugging in. See what I have outside. Negative 3, what does it be?
okay, so we're using, and which one of these equations are you using at this point?
I'm using the 0 equals negative x times.
Yeah, let's keep it factored. So we can just look at what's happening here, here, and here, and then just multiplying. Yeah, I think keeping it factored is a good idea. All right, so let's try. So we're trying, you said x is negative 4. So if I take that negative 4 and I plug it into here, is that positive or negative? Okay, so that's positive followed by a negative, followed by a negative. What is a positive times a negative times a negative? A positive. Okay, over here. Okay, try x equals negative 1. When we plugged in negative 1 here, we get, okay, gives me positive, followed by a negative, followed by a positive. What is a positive times a negative times a positive? A negative. What does that mean? Actually, let's finish this. Let's finish this. What about over here? Okay, so try x equals 1. When we plug in 1 here, that's negative. When we plug in 1 here, that's a negative. Oops, why is that circled? So you have a negative and a negative. And if I plug in 1 here, what is a negative times a positive? A positive. And then over here, okay, so try x equals 4. When I plug in 4 here, it is negative, followed by okay, so a negative followed, oh man, that's sloppy. Negative followed by a positive, followed by a, what is a negative times a positive times a positive? And negative. So my graph is, you identified x is -3 as a maximum point. Because the graph is positive here, followed by the graph being negative over here. I agree with you that it is a maximum, but you're having a hard time identifying whether this is a global or whether it is just a local. So we do know that x equals -3 is a max. Now let's look at the whole thing. We have a graph that is a positive slope, positive slope, positive slope, up to this particular point here, becomes negative, and then it becomes positive, and then it becomes negative. Now, one of these is, we do have a global max, but we need to find out which one is the highest max. How do I find out which of these is the highest max? Either, do we agree that x is 3 is a max as well? How can we tell whether x is -3 or x is 3 is the highest max?
Would we plug it into our original equation?
Yeah, and that'll tell us, into our original equation, and it'll tell us our y value. And whichever y value is the highest will be, that will indicate to us which one is the highest max. So that's what we have to do. Okay, so let's plug in, if I plug in this -3 here, let's plug in the -3 here. So so we know that x is 3 is a max as well. One of these is a local max and the other is a global max. So we're going to figure out which one is which. So we're going to plug in the -3. So I have -1/4 times -3 to the power of 4 plus 9/2 times -3 squared plus 5, and compare that to -1/4 times 3 to the power of 4 plus 9/2 times -3 squared plus 5. Which one is going to give me a higher y value? It's the same. It's the same, because this is to the power of 4, which is going to make it positive. This is squared, which is going to make it positive. Actually, this is supposed to be positive anyway down here. So they're going to be the same. So we can actually have two global. If they're both the same, we're going to say both of these are global. So x equals -3 is both of these are global. Okay, what's happening when x is 0? It's a min. Yeah, we have a graph that's negative followed by a positive slope, so that's a min. What kind of min is it? What is it? I hear global and I hear local. What's happening over here? This is positive, 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 followed by a negative, followed by a positive, followed by a negative. Is there a minimum at all? Is there a global minimum at all? This just keeps on going down, down, down forever. So this has to be a local, not a global. There's no global here, global minimum at all. You guys see that? So this is a local. This is a local. Okay, now we still, is time up? Is the time up? Did we find any inflection points? There's an inflection point at this for the square root of 3 and negative the square root of 3. You should be able to find two non-stationary inflection points at the square root of 3. So x equals the square root of 3 and x equals negative the square root of 3 are non-stationary inflection points.